We're now going to look at computational problem 2 from test number 3. Capacitor is charged to a voltage V0. The capacitor is then disconnected from the power source and connected to a resistor R. How much energy is dissipated through the resistor? Recall, the total energy is the sum of all the power dissipated for all time, so your answer will almost certainly have to involve integrating some quantity from t equals 0 to infinity. How does the energy stored in the capacitor change over the same time interval? Okay, so a capacitor is charged to a voltage V0. Capacitor is then disconnected from the power source, connected to resistor R. So what do we have? We have this. We have a capacitor, we have a resistor, and we have some switch, which is going to close at t equals 0. So we know that our Q0 is just going to be equal to CV0. And that just says this is exactly the same as saying a capacitor is charged to a voltage V0. That means it has this much charge, Q0, CV0. Okay, now what else do we know? From our equation sheet, we know that this is going to be a discharging capacitor, and we know that Q of t equals Q0 e to the minus t over RC. All right. How much energy is dissipated through the resistor is what we're asked. Well, what is the power dissipated through a resistor? I'm worried this blue might not be showing up as well, so I'm going to switch a little. So what is the power of a resistor dissipated through a resistor? That is I squared R. And what is the energy compared to the power? It's just this power integrated over time. What is that time? Well, it starts at the time when we close this switch, and it ends when the capacitor is completely empty, which is basically infinity. Okay. So now all we need to do is figure out what these things are. Well, we're given R. We know what this is. We're given this C as well. We're given R, but what is I? Well, we don't directly know I, except that we're given charge as a function of time. And what is the definition of current? It is dq dt. So our current is just dq dt, which is minus 1 over RC Q0 e to the minus t over RC. I'm going to pull that over here. Okay, so this is dq dt, which is I. By definition, this is I. All right, so now we have current. Now we have resistance. Now we're done. The problem's over, okay? So all we need to do is just plug everything in now. So I'm going back to the black pen after all that. Okay. All right. So what is I squared R? I squared is just this squared, so that is 1 over RC squared. I'm getting rid of the minus sign because minus by minus is a positive. Q0 squared e to the minus t over RC, except there is a 2 here because this is squared now. So e to the minus 2t over RC, and then that's I squared. We're going to multiply this by R, and now I'm going to take the time integral of this whole thing from 0 to infinity. And let's just pull out those things that we know do not change. We know Q0 is a constant, R and C are constants, so I can pull all that out. So the only thing left under this, and I'm going to move this again. The only thing left under this is we have, let's see, I think I will do it like this for now, yeah. So R over RC squared, Q0 squared, and then I have e to the minus 2t over RC dt. Well, if you look on the equation sheet, you will see we have an equation that says e to the minus alpha t 0 to infinity dt is just equal to 1 over alpha. So what is our alpha then? It's 2 over RC. So this is equal to RC over 2. So now I'm going to go ahead and simplify this over here. So we have RC over 2. I'm going to now put this other R in there, so it makes R squared. And I have an R squared C squared here, Q0 squared, and I believe we're done. This equals I squared R. Let's take a look at it though. So make sure R squared C 2 R squared C squared Q0 squared. Yep, that looks good to me. Okay, so R squared cancels our R squared. One of these C's cancels this. We have 1/2 Q0 squared over C. So this is the power dissipated through the resistor. Now, there's all sorts of different ways that you can do this. Some of you might already have recognized this. The next part of the question is, how does this compare to the change in the energy stored in the capacitor over this same time interval? Well, what was the initial energy stored in the capacitor? If you look on the equation sheet, you will see that 1/2 Q0 squared over C is the initial energy, U initial. What's the final Q in the capacitor? Well, 1/2 Q squared over C. This is the initial because it's Q0 at the beginning. Actually, I think you guys know I kind of like a different expression for this, so I'm going to go ahead and write that right now, and I'll just say this is 1/2 CV0 squared over C, which is 1/2 CV0 squared. So this is our initial energy right there. So what is our final charge? Either one of these expressions works. Well, what's our final charge in the capacitor? It's 0. So what's our final energy? 0. So what has happened between U final minus U initial is just equal to minus 1/2 Q0 squared over C. The exact same amount of energy that was dissipated in the resistor. Okay, there you go. That's computational problem number 2.